right, a few announcements. One, I think I may have announced this last week, but I didn't know it was going to extend so long. Remember, did I tell you all about the possibility of fire alarms going off? Okay? I didn't realize that could go on through tomorrow. So that wasn't just last week, it's this week too, through Wednesday. Okay, so if you hear the alarm go off anywhere on campus, don't panic. They're just testing the system in every building. And if you smell smoke or see fire or hear someone say, this is not a drill or a test, get out, okay, then we do that. But otherwise, we don't pay it any attention at all. Seldom will I ever tell you that, but this time we will, okay? And next week coming up is Cougar Connection Week. And there's going to be lots of activities, both campuses, good programs, and there'll be opportunities, groups here that you can sign up to volunteer for. There will be campus organizations you can sign up to participate with. There's just going to be a lot of good things going on. Both campuses, Monday, Tuesday, and Wednesday. Thursday of next week, I think most everything is on the Birmingham campus, but it's all good stuff. So I'll tell you more about it next time when it's the last time we'll meet before it starts. Okay. Anything else? I can't think of anything. Any questions on anything so far, either math or otherwise? Okay. All right. We were talking about finding the zeros of a function, and we actually did the zeros of the A one there, okay? How do we go about doing the zeros of B? G of x is equal to square root of 10 minus x squared. Now, I don't always do it myself, but I always try to at least note it and think about it, is when you see a problem like that, number A, what is the domain of A? All real numbers. Okay, is that true of B? No. So I like to always write it down, even though sometimes I forget to, and indicate to myself what the limitations on the domain are. So you tell me, what are the limitations of that domain, or are there any? Say again? Okay, what's inside the radical has to be positive. So let's write that down just as he said it. 10 minus x squared, that's what's inside the radical, has to be positive. Well, actually, it can be 0, but how do we write that mathematically in math speak? I don't want to write all those words. I'm too lazy for that. Oh, greater than or equal to 0. Good. Now, what can we do from there? We need to know the limitations on x, not on 10 minus x squared. So what do we do? Anybody? Help me, I'm drowning. Okay. Say again? Okay. Do what? I fit my hearing. Okay. Yeah, the 10 minus x squared has to be greater than or equal to 0. How do we solve that for x? That inequality. A lot like we would an equality equals equation. Say again? Okay, and how would you do that? I just pick it up and move it? No. What? Subtract 10 from both sides. Excellent. Okay. All right, and that gives us, that goes to 0, minus x squared is greater than or equal to negative 10. Okay. Next. Divide or multiply by negative 1. Very good. So that'll be x squared. This will be 10. Oh, I forgot to put the sign in the middle. Say again? You have to flip it. Anytime you multiply a directional inequality or divide a directional inequality by a negative number, you have to reverse the direction of inequality. Not adding or subtracting. You can add or subtract, positive, negative, anything stays the same. You can multiply or divide. Any positive number stays the same. You multiply or divide by a negative number, flip that inequality. So that becomes less than or equal to 10. One more step. Second? Yeah, take the square root of both sides. And that gives us x is less than or equal to Say again? Say again? I can't hear. Square root of 10. Now, most of the time, if you take if you take the square root of both sides of an equation, you have to account for plus or minus. So should I put plus or minus square root of 10? It can't be minus. Well, wait. The expression can't be, so let's just put square root of 10 and see what happens with that. All right, JT is here. All right. Anyone else coming since I called roll? Okay, actually we have to do a little thinking on it. Oh, shucks, that. Okay. Let's just think. Let's pick something less than the square root of 10. Okay? Like 3 is less than square root of 10. That would work perfectly. Be fine. Okay? Now, minus the square root of 10, if we did something less than the negative square root of 10, that would be something like negative 4, right? Would that work if we put in a negative 4 there? X equal negative 4. Negative 4 squared would be, bless you, 16. And 10 minus 16. Okay, so you're absolutely right. You need to stay with the positive. So keep that in mind. X less than square root of 10. Well, but it also has to be greater than negative square root of 10. Okay, so we basically just said that, but you need it on both sides because really the plus or minus does come into play there. Because anything outside of that on either side is going to give you a negative in the radical. So you have to be between minus square root of 10 and positive square root of 10 for that to work. Okay, does that make sense? All right. Okay, that's just to keep, all right, here's Walt, right? Okay, I know you're in here, but you're hiding on me. There you are. Good deal. Okay, so now that we got that established, let's actually do the problem. Find the zeros of the function. So what would we do? Did I hear someone say something? Oh, they were just talking. Okay. What do we do? Find the zeros of the function. What does it mean to be a zero of the function? I know it was at least 5 days ago, so it's been a long time. So how do we find the zero of the function? How would he set it up to do it? Say again? Set it equal to 0. I thought I heard someone say that. Okay, set that equal to 0. Okay, now, what's the next step?
We get everything on one side.
Say again?
We get everything on one side.
Well, everything but 0 is on one side now, so we're all right there. But how do we solve that? We're wanting to solve for x. Find the values of x. Say again? Not yet. What's in the way? The square root sign. So what do we have to do first? Square both sides, okay? When you square 10 minus x squared, what do you get? 10 minus x squared, okay? And when you squared 0, what do you get? Oh boy, y'all are good. Okay, now, anytime you square both sides of the function, flags should rise, bells and whistles should go off to warn you, you better check your answers. Because you may have introduced what they call an extraneous solution. So we'll need to do that at the end. So, let's continue. Now what do we do? Yeah, add x squared to both sides. Okay. Yeah. Where is it? Okay, there it is. And what does that give us? I'm going to reverse sides here. X squared is equal to 10, and x is equal to plus or minus the square root of 10. And they both fit because they're both in our domain. Right at the ends of the domain, but they're there. The equal signs are there. So we're okay. Okay. Now, we sort of need to check them. I said we need to check, but we already did that, didn't we? When we were checking for a domain. And we found out they work. So yeah, they still do. They're in the domain, so we're all right with that. All right. Want me to erase this chicken scratch here and go on to H or C or whatever it's called? Or you want to keep it up there? Anyone need it? Okay. I'll erase that so it'll be a little easier to read the next. All right. H of t is equal to 2t minus 3 over t plus 5. Okay? Now again, the book doesn't do this, and you don't have to do it, but it's a good practice to do. What's the first thing you probably ought to do? Well, what t cannot be. So you tell me what t cannot be. Okay, t cannot equal negative 5. Okay? Every other t is perfectly fine. All right. Not going to make a difference in this one, but you may not have known that ahead of time. We're looking for the zeros of h of t. How do we do that? Set it equal to 0. And since I've written that over there, is 2t minus 3 over t plus 5 is equal to 0. Now, there's two ways you can approach this, okay? And both ways are fine. How would you approach it? You may even come up with a third way. I don't know. How would you approach that? Sneak up on it? No. Okay. Say again? Okay. Say that one more time. Multiply, is that what you said? Yes, yes, exactly. That's one way to do it. Multiply both sides of the equation by t plus 5. That works in most states, okay? All right. What it does on the left is eliminates the denominator. Always in favor of that. What does it do on the right? Becomes 0, right? So now we have 2t minus 3 is equal to 0. Because multiply anything by 0, and you still get 0, okay? Now, that leads to the second way to do it. And this is the way I usually do, just because I'm pretty lazy, okay? When I see a fractional form like this, and I know it's going to be equal to 0, that means the numerator's got to be 0. It doesn't matter what the denominator is. 0 over 5,843,000 is still 0, okay? So it doesn't matter what the denominator is, as long as it's not 0, but we already have taken care of that. So basically what I would have done was go straight to this, say the numerator's got to be 0. The only way for a rational expression to be 0 if that numerator is 0. Does that make sense? So I went straight there, but either way will work. What do you do from here? Add 3 to both sides. And that gives us 2t is equal to 3. Divide by 2. And you get t is equal to 3/2. Now, I'm pretty sure I got zinged on the student course evaluation sometime not too long ago. I think it was last spring or maybe last fall, that I was treating it like a high school class. And maybe some of you think this too. And I bet you this is part of the thing, going through every step like that. Is that completely redundant and unnecessary, or do you like seeing those steps? You do like seeing. Okay, I'll continue to do it. I just didn't want to just say, oh, it's obvious, books do that all the time. And it's intuitively obvious that this is the answer. How did you get there? So I like to show the steps when I'm teaching anyway. When I'm doing it on my own, I skip like crazy. Okay, so there we found the one and only 0 for this one. We found 2 zeros for that one. We found 2 zeros for the other. And let's see how the book did it. Okay? If they did it any differently. Oh, was it all right to erase? Sorry, can't get it back, but okay. So, okay, impossible for me to get back. But we're going to see it right now. So here's the A. To find the zeros of a function, set the function equal to 0, just like you were saying earlier, and then solve for the independent variable. So for the first one, we set f of x, which is 3x squared plus x minus 10, equal to 0. And now, again, this may be too elementary, but I like to say it anyway. Anytime you have your variable to a power other than 1, we'll say, then get everything on one side, the other side equal to 0. That's going to be the way to go. If your variable is equal to 1, then get the variable on that side, get everything else on the other side. You have two different techniques depending on the exponent. If it's 1, get everything on the other side. If it's other than 1, get 0 on one side. We already got 0 on one side. What's our next step? Factor. Very good. Okay. And sure enough, they factored it without showing you how they factored it as 3x minus 5 times x plus 2. I'm pretty sure that's what we did last Thursday, but who can remember that long? Okay. Then what do we do? Once we factored, why did we do that? What difference does factoring make? This makes it more complicated, make it longer. Why did we factor? Yes, because now we have a product of two entities equals 0. One or the other's got to be 0. So we set each of them equal to 0. First we'll do the left-hand side, and that gives us x equal 5/3, without showing you how, but it gave it to you. And the second one gives you x equal -2. There's our two zeros right there. Okay? And then I think they probably write it as the zeros are that. Note that the graph has those two intercepts. 2, 0, 5/3, 0, and -2, 0. Yep. It's a parabola. Anything that's quadratic is going to give you a parabola. This one opens up. Does anyone know how you can tell it's opening up and not opening downward? Anyone know that? Yes, because the leading term, the leading coefficient is positive, so that means it's opening up. Good idea. You aren't supposed to know that yet, but it's great that you do. And these are the x-intercepts. The zeros produce x-intercepts. To write them as zeros, x equal 5/3, x equal -2. To write them as x-intercepts, 5/3, 0, -2, 0. How did you know the second one was going to be a 0? How did we know these were zeros here? Say again? What? Look what? What? Okay, I can't hear.
Looks like it's coming from the point of origin.
Yeah, okay. So they're on the x-axis to mean y is 0. But how else? How do we get it? We said this equals 0. And what is this? What is f of x? Y! And this is an x-y pair. When you set that y equals 0, you know those have to be 0. That makes them x-intercepts. It all goes around in the same little circle, and it makes perfect sense, right? Yes, math does. Okay. Good deal. I'm glad y'all agree. Okay. So that's the first one. Sorry, I'm taking way too long on this. On the second one, we set it equal to 0, just like before. And then you square both sides. And they don't warn you on this. You really, every time you do that, remember, check both answers. Check your answers, okay? Because you may have introduced an extraneous root, okay? Then they did it, yeah, they did exactly like you did. Added x squared to both sides, and then take the square root of both sides. And that gives you x equal plus or minus square root of 10. Now, they drew the picture which showed kind of the same thing we were talking about before. The zeros are that, and the zeros fit our domain. Okay, they never showed you the domain until basically they got here and see that's the only values they're allowed between minus square root of 10 and plus square root of 10. We did that up front. Okay? What is that, by the way? Anyone know? That shape? It's what? A semicircle, exactly half a circle. You're absolutely right. And how could you tell that? Let's go back to I'll write it down here. Our original thing was f of x, or no, it was g of x, wasn't it? Whatever it was. G of x is equal to the square root of 10 minus x squared. Okay? Now, what's g of x in this case? Okay, not for this one. Why? Why not? Okay, it's y. So you can write this as y is equal to the square root of 10 minus x squared. And then guess what I'm going to ask you to do next? Second? Not yet. No, we're not doing that. We already did that. What would you do next to make that look nicer? Square both sides. And what would that give you? Y squared is equal to 10 minus x squared. Okay, next thing I think I'd ask you to do would be to move the x squared to the other side. So let's add x squared to both sides. And that gives you x squared plus y squared is equal to 10. Does anyone know what that formula represents? A circle. Anytime you have the same coefficients for x and y, x squared plus y squared, 7x squared plus 7y squared, anything like that. But if you get it, x squared plus y squared is equal to blank, guess what the blank is? R squared, the radius of the circle squared. That makes the radius square root of 10. No, R squared is 10. The radius is square root of 10. So square root of 10 here, square root of 10 there, square root of 10 there. Everywhere, square root of 10 from the origin. Now, is that a function? X squared plus y squared equal 10. Is it a function? The one I wrote there. X squared plus y squared equal 10. Why not? Who said no? Okay, why not? Okay, because y is squared, that's one thing. Also, picture it. Vertical line test flops badly, fails, okay? So, that's why we had to have the square root. That's a positive square root. G of x equal positive square root of 10 minus x squared. They couldn't just say g of x squared plus x squared is equal to 10. That would not have been a function. Would have been a relation, but not a function. All right, very good. Beat that to death, didn't we? Okay. Do I need to leave that up a little longer? Okay. Let's go to the third one. What you reckon they're going to do? Exactly what you did. They multiply both sides by t plus 5, but didn't show it to you. Okay? Got the same answer. Or, just look at it and say, if that's equal to 0, the numerator's got to be 0. Either way gives you the same thing. Okay? So, and then, really easy to solve for t. And they took every step on this one, okay? T is equal to 3/2. Make sense? The last one, when it was 5/3 something, they did 5/3. But this one, they did all the steps. Any questions? Have what we need? That's example 3. So the 0 of this one is h is equal to, of h is t is equal to 3/2. Now, this is not the entire graph of this function. Okay, that's just part of it. If we were going to do the other part, it would be like this. Something like that. Okay? It doesn't have a 0 because it never reaches the x-axis again. Okay? We'll talk about this later. Section 2.6, we'll do problems such as this, and we'll know how I knew the other half of the graph goes like that. All right? Some of you may already know. All right. Ready to move on? Okay. Now, there's a checkpoint at the bottom of the page. Please do those as soon as you can. Okay. Now we're moving to increasing and decreasing functions. All right. Let me say this. Just looking at a function, it's going to be really hard to determine whether it's increasing or decreasing. That's why this is put in this section, 1.5, analyzing the graphs of functions. Because once you graph a function, it's really easy to see whether it's increasing or decreasing. Just looking at that mess of algebraic symbols, not really any easy way to tell until you get to calculus. And then it's all easy, right? Okay. So, the more you know about the graph of the function, the more you know about the function itself. Consider the graph shown here. Rather bizarre looking function here, but certainly could be. This is what we call a piecewise defined function. One piece is defined over there for any x less than or equal to 0. Next piece is from 0 to 2, and the next piece is from 2 to positive infinity. Nope, it's not. It's 2 to 3, sorry. Or 2 to 4, whatever it goes to. Okay? So, we have a fixed domain here. 3 pieces in the domain. Okay? As you move from left to right. Now, here's the key, folks. I see some people do it, and I cringe, but I can't get them not to. Remember, we're always moving left to right, from negative to positive. So when you're moving from negative to positive, this function here is decreasing, because as your x is increasing, your y is going down. Make sense? Here, it's constant. As x is increasing, y never changes. So that's a constant part. And over here, when x is increasing, the y is also increasing, so that's an increasing function. I've seen some people do, well, you start here, and when you're going this way, that's increasing. When you're going, no, you always go the same direction, from negative to positive of x, always increasing x, and then what you're telling is, what's the function doing? Because what's the function? What's f of x? Y. What is the y doing when x is increasing? That's the question you ask yourself. As you move left to right. Remember, you always move left to right on x, then you're determining what y is doing. Does that make sense? All right, good deal. All right. This is awkward to get through here, but I've done it. Okay. So, here's how we say it mathematically. A function is increasing on an interval when for any x1 and x2 in that interval, remember that x1 has to be less than x2, so you're going from x1 to x2, implies that the f of x1 is less than f of x2. That means the function is increasing. The y's are going up as you're going from left to right in x. A function is decreasing on an interval for any x1, x2, such that x1, again, is less than x2. Then when you go from x1 to x2, if it's a decreasing function, the f of x1 must be greater than the f of x2 because it's decreasing. The y's are going down as the x's are going up. And it's constant any interval, on an interval, when for any x1, x2, and it really doesn't matter which is greater or less now, they're always the same. F of x1 is equal f of x2. That's a constant function. Okay? Makes sense, right? Okay. So, you use the graphs, and boy, that's really easy, to describe the increasing or decreasing or constant behavior of each function. Now, I think I'll go over to the other side. Okay? On that first one, f of x is equal to x cubed. Is that increasing, decreasing, or constant? It's increasing certainly down here, and certainly over there, because f, it's going up from left to right. Only place of any question might be right in here. Is that constant there or not? Well, it looks almost flat, but if you were to take a value at x, say 0.1, okay, or negative 0.1, okay, negative 0.1, plug that in here, and what do you have? Negative 0.001, okay, tiny little number, but still negative. You go a little bit further to the right, it goes up a little bit at 0, and at 0.1 over here, it's positive 0.001. So it's not going up by much, but it is going up very gradually. So that is always increasing. Even though it looks sort of flat there, it's not. Okay? How about this one? Describe to me its behavior. Say again?
It increases and decreases and increases.
Okay, he said it fairly generally. Let's get some limits on there. In fact, let's do it for the first one too. I realized I sort of left that kind of vague as well. Where is that first one increasing? Okay, describe the increasing and decreasing. Okay, where is this one increasing? We said increasing from And you always reference the x from negative infinity to positive infinity. All real numbers is increasing, okay? You always reference the x. You're looking at the y to see what it's doing, but you're giving the interval on x's, okay? So do that same thing for me here, the b part. You said it's increasing where? From negative infinity to, say again? You're referring to the x value, -1, and it doesn't matter here whether you put parentheses or bracket. Most of the time when we're talking about intervals of increasing, decreasing, they put parentheses, okay? Is that the only place it's increasing? Oh, where's another one? From 1 to positive infinity. Is it decreasing anywhere? I thought he said it was. Where? -1 to 1. Perfect. Y'all are good. Does everybody see that? And that's how we express it. Increasing on this interval and that interval, decreasing on that interval. Okay? That other one, increasing everywhere. Okay? How about this one? The C one. Increasing from negative infinity to 0. Excellent. Constant from, second, 0 to 2. Excellent. And decreasing from 2 to positive infinity. Excellent. Y'all are good at that. Does everybody see that? Okay? That's how we express it. You always are looking at what the y is doing. That tells you what increasing or decreasing, but you give it on the intervals of x. Always give it on the intervals of x. And x is always going left to right. Negative to positive. Small to big. Okay. Make sense? Okay. That was example 4. Oh, and there's a checkpoint at the bottom of the page, so do that at your earliest convenience. Oh, here they're going to do it. The function is increasing over the entire real line, and they just say it in those words. Okay, sorry, I introduced how to write it. They're just saying it, okay? Increasing, but no, they say increasing on an interval, negative infinity to -1, decreasing on an interval, -1 to 1, and increasing again from 1 to positive infinity. Exactly like we said. All right. Huh? Yeah, got it. Good deal. Okay, folks, we're just missing 1, 2, 3, 4, 5, 6, 7. Okay, so 30 people here anyway. Good deal. All right. And the C one, function is increasing on the interval from negative infinity to 0, just like you said. Constant on 0 to 2, and decreasing from 2 to positive infinity. Any questions? Got it? Okay. To help you decide whether a function is increasing or decreasing or constant on an interval, you can evaluate the function just like we did that one that looked like it might be constant there. Pick some values where you think it may be one thing or another. Plug them in, see what the function's doing. See what the y is doing. The f of x or g of x. Okay. Now, you need calculus. Oh, underline that. You need calculus. Everybody needs calculus to determine for certain all intervals on which it's increasing, decreasing, or constant. There is a way to do it in calculus. It's just so handy. In fact, that's why Newton did it. He was tired of doing all this long stuff. He was lazy and wanted to find a better way to do it. Okay, never mind. All right, the points at which the function changes its increasing, decreasing, or constant behavior are helpful for determining relative minimum, if it's the low point, or relative maximum, if it's a high point. Okay? So here's your definitions for what your relative maximum, minimum, and relative maximum are. A function f of a is called a relative minimum of f when there exists an interval from x1 to x2 on either side of a, okay, such that x1 is less than x2, and it implies that everywhere in that interval from x1 to x2, f of a is always less than or equal to the other f of x's. You can't get any lower than the f of a on that interval. Okay? That makes it a relative minimum. Okay? Be a relative maximum if you have an interval from x1 to x2, and where x1 is less than x2. It implies that f of a is greater than or equal to all the other f of x's there. That means it's a relative maximum. Okay? Does that make sense? Okay. Any questions? All right. Let's see. Yeah, here's one. Here's a figure, 139. It's 137 in your text. I don't know why it's 139 here. Must be, they didn't update it. Okay. Now, they don't have any coordinates listed, so we can't name the coordinates. If they did, we would. Okay, but they don't. So, here's a relative minimum, because for any x somewhere around that a value there, the f of a is always less than or equal for all of your other f of x's, anywhere close to. Over here, though, let's make this be b. F of b is always greater than or equal to all the f of x's close by. That makes it a relative maximum. Here again, as we named this c, here this is a relative minimum because all your other f of x's are greater than, in other words, your f of c is less than all the other f of x's. And up here, another relative maximum because all your other f of x's, your f of c is greater than or equal to all the other f of x's close by. Now, we can't say all other f of x's. That's why we say relative. I said close by because if you're looking at this one, if you go far enough away, you can find f of x is greater. But don't go far enough away. Stay close by. For some interval between x1 and x2, that this is the maximum one, as high as it goes, then that's a relative maximum. The others we call absolute maximum. We're not getting into that. You'll get into that in calculus. Okay. Now, I think we're ready for example 5. Oh. Trying to find, oh yeah, this statement is here. You'll study a technique to find the exact point in which a second degree polynomial function, what do we call a second degree polynomial function? That's sort of a special name. They named the formula after it. Say again? Quadratic. Yes, a quadratic function, second degree polynomial function. It's so much easier to say quadratic. Second degree polynomial. Okay. Quadratic function to find where it has a relative maximum or minimum. They're really easy to do. We'll do that in the next chapter. Okay. For the time being, however, we can use a graphing utility to find reasonable approximations for these points. Okay? If you have a graphing utility. You may not. That's okay. You can still do it pretty much by hand. You won't maybe get as precise. And they skipped it. Okay, so let's do example 5. Okay, example 5. It said use a graphing utility, but again, we can do it without one. To approximate the relative minimum of the function f of x is equal to 3x squared minus 4x minus 2. Okay. What kind of function is this? Say again? It's a polynomial function. I heard that perfect. Yes, you're absolutely right. How about a little more precisely? What order of a polynomial function? What degree of a polynomial function? Second. Very good. Okay. And what do we call a second degree polynomial function? A quadratic function. Okay. Now, what is always the graph of a second degree or a quadratic function? Does anyone know? Parabola, exactly. And somebody already knew how to tell whether it's opening up or opening down. How was that? What is positive or negative? The leading coefficient. And what is the leading coefficient here? Say again? Positive is 3. That's the 3. Leading coefficient, largest degree. So, what does that tell us? It's opening upward. So, we're looking for the relative minimum. If it's opening upward, it has to have a relative minimum. Not going to have a relative maximum because it keeps going and going and going. Okay? So, we're looking for a relative minimum. So, what I would do is pick a few values, and I like to pick the really easiest ones I can, and then start getting to smaller and smaller numbers. So what's the easiest x to choose? Easier. Second? 0. Okay? All right. Is it Jalen? Okay. All right. There you are. All right. We're only missing 1, 2, 3, 4, 5. There you go, folks. Okay. So let's do f of 0. Anyone tell me what that might be? -2. I love 0 because it's so easy to do. Because the first is 0, the second 0 is -2. All right. That sounds like it could be close to the relative minimum. We don't know. Okay, what's the next easiest? Someone said it earlier. Yeah, let's try f of 1. Okay? And f of 1 would just be, real easy, your coefficients. It's going to be 3 minus 4 minus 2. Because if you put 1 in for x squared, that's 1. 1 in for x, that's 1. So you just multiply by 1. That's 3. Okay, what does that give us? Negative what? 3. Okay? That's -6, positive 3, -3. So we think the relative minimum is going to be closer to 1 than it was to 0. Okay? So where do you want to head from here? We can continue up to 2 or go to some fractional form. I thought you'd say so. Okay, let's go to 2. F of 2. And what would that be? This one you have to think a little bit about. Second? Okay, f of 2. 3 times, what is 2 squared? 4. 3 times 4 is 12. Minus 8, that would be 4. Minus 2 would be 2. Okay. We're bigger numbers. Okay? So, I'm guessing now we need to go back and do, second? Yeah. Negative, well, no. We know it's closer to 1. There's only going to be 1 0. And if it's, if f of 1 is at -3, this is going up from there. -1 is not going to give us, it's going to give us something greater. Over here it's going to be greater. We just saw that. So it's probably going to be between 0 and 1. Okay? So I'd go to a 1/2. And then if that was, less, then, just keep sandwiching in and use as much time as you need. I'm not going to use it in class time, but let's see what we get. And sure enough, they got 0.67. So if we had gone to 0.5, which would have been the next thing we would have tried, we'd have probably gotten something even closer. And then we'd go between that and 1, and you get something closer. And we might back up some. Yeah, okay. You keep going back and forth until you get as low as you can go. And this isn't technically called this, but I consider it the method of exhaustion. When you get tired of doing it, stop saying, it's close to this, this method of exhaustion. Okay. You can use a graphing utility, it's a lot quicker. Okay. There is a checkpoint. Please use that as well. Do that as well. Now we're ready for average rate of change. All right. Ever seen this before? Have any idea what we're talking about? Believe it or not, we just did it not long ago. We had a different name for it. Average rate of change. Let's see, what can we mean by that? We have learned that the slope of a line represents its rate of change, right? Because how much is it going up or down as you go right or left? That's your slope, isn't it? Change of y over change of x. Hey, where did we just do that? Okay, we called it difference quotient. Okay, we're doing the same thing here Only a little bit different emphasis, but it's the same thing. We're looking at the slope of a line. For a nonlinear graph such as this, you approximate the rate of change using the graph, using a line, okay? So for nonlinear, the slope of change at each point, if you have x1 f of x1, x2 f of x2, well, all you can do is the average rate of change between those 2 points. Because notice, not like this room setup, okay. Notice here, the slope is here, here it's there, 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 and here it's there. Some places positive, some places negative, plus the average rate of change between here and there. We'll take the y value here, the y value here, the difference there, over the difference in x. Change of y over change of x, that's your slope of your tip. And we call this the secant line, the slope of the secant line. Okay? So for nonlinear graphs, the slope changes at each point. The average rate of change between any 2 points, x1 and f of x1, is the slope of the line through the 2 points. And we will call that, and here it says, that line is called the secant line. Okay. One reason I don't stay over there is my microphone's in my computer. I'm not sure how much it picks up. Okay. Any line through any 2 points is called the secant line. And the slope of that line will sometimes say m sub sec, S-E-C. S-E-C, and that's not the same one. Okay. The average rate of change from x1 to x2 would then be the y at x2, the change of y at x2 minus y of x1, y1, y2 minus y1, over x2 minus x1. That's your slope, just like we did before, but now we're talking about the slope of the secant line. Change of y over change of x, that's your slope of the secant line.
So basically you just go out from the y minus y1 over x2 minus x1.
That's it, exactly. That's exactly it. Okay? Remembering that we are assuming x1 is always less than x2. So you have to do those y's. Whatever the y's are, yeah, do them in that order. Okay. So here's example 6. Oh, did you need that longer? Oh, okay. Anyone need it longer? Okay. Sometimes I get going too fast. So example 6 on page 54. This. All right. Find the average rate of change of f of x equal x cubed minus 3x from x1 equal negative 2 to x2 equal negative 1. So how are we going to do the average rate of change? What was that formula? Okay. F of x2 minus f of x1. You said y, which is perfectly fine, but since we're in function speak now, okay, we'll say f of x2 and f of x1, which are y2 and y1, over x2 minus x1. Okay, very good. Now, in the first one, in the A part, what are we going to have to do first? What's the first thing you see right here? Yeah, you got to see what f of x2 is. Well, your x2 is negative 1, so your f of negative 1, right? That's what you got to do first, f of x2. What is f of negative 1? You tell me how to do it. Okay, negative 1 cubed. Now notice we put that in the parentheses, okay? Negative 1 cubed. In my Math 100 class, they were doing polynomials. No, they're not. Yeah, they are. Doing polynomial stuff. And when they see a minus sign in front of a parentheses, they bring it in and square it and cube it, and they get wrong answers. You leave it outside if it's outside, but if it's inside, keep it inside. Okay, for now anyway. Minus 3 times negative x1. Okay? And what's negative x1 cubed? Second, negative 1. And what's negative 3 times negative 1? Plus 3. So that's going to be Help me. 2. Okay, so that is 2. Alpha of x2 is 2. Your x1 here is negative 2. So we need to do alpha of negative 2. I got the numbers backward, but you follow it. X1 is negative 2. So what is alpha of negative 2? Go back to this. Negative 2. What do we with it? Cubed. Minus 3 times negative 2. Perfect. And what's negative 2 cubed? Negative 8. Okay. And negative 3 times negative 2? Plus 6. So what's this? Alpha of negative 2? Negative 2. So this is going to be negative 2. And then x2 is minus 1. Okay, so I think we can do. So the first average rate of change for A is going to be alpha of x2 was 2 minus a negative 2 divided by x2 was minus 1 minus, and x1 was a negative 2. Okay? They like having minus 2's, don't they? What's the numerator? Numerator? 4. Denominator? 1. 4 over 1, 4. So the average rate of change from x equal negative 2 to x equal negative 1 is that really steep line over there. You see it? Really steep. Slope of 4. Ooh, goes way up fast. Okay, yeah. There's negative 2, negative 2. That's what we found here. When it's negative 2, it's negative 2. And when we plug in negative 1 here, we found 2. And sure enough, there's negative 1, 2. And the slope of the line in between there is a steep 4. Okay. Make sense? Okay. How about the B part? Now, I don't want to erase this. No, I do, too. Because in the old edition, they use one of the same points, and I didn't want to erase it. Now they do 2 new points, so I will erase it. So I want all of you to get this first. Make sense yet? Yes.
So I'm just confused with the question asking.
Okay.
Just asking for the slope.
Not hearing so bad.
You're just asking for the slope from A to B.
Yeah, the slope from the A part is asking you for the slope from x equal minus 2. So come back here to minus 2, find the graph. Now, I didn't draw the graph. You could have gone straight to the graph and found the y value there is negative 2. Okay? I use this to plug in negative 2 here, which I did right here, and found out it was negative 2. So you see what I did verified what the graph showed. So you could either use the graph or do the calculations. I wanted you to practice doing calculations. X2 was minus 1, and when you plug in x2 and minus 1, did the math, it came out plus 2, and sure enough, at minus 1, you're up here at plus 2. And then you do the slope between those 2 points, y2 minus y1, 2 minus a minus 2, that's 4, going up 4, and you're going right 1. Negative 1 minus a minus 2 would be negative 1 plus 2, which is plus 1. So that gave you a slope of 4. Okay? Does that answer what you were asking? Okay. Yeah. You were saying it right. You're doing the slope between those 2 points. Okay. If you don't have the graph, you calculate the points. If you have the graph, you could have just gone there and looked. That's too lazy. Too lazy. Too lazy. Can I erase this and do the B part? Okay. All right. So let me erase and do the B part. All right. The B part, we're going from x1 of 0 to x2 of 1. So what is our formula for average rate of change? Alpha of x2 minus alpha of x1 over x2 minus x1. It's y2 minus y1 over x2 minus x1. Same as before, but we're now calling y's f. Okay. So your x2 was 1. So what's your f of 1? Let me go up here. F of 1. What is it? Say again?
0.
Really?
Is that the one right from B?
Say again?
You said B, right?
Yeah, but I'm doing alpha of 1, which is your x2. Alpha of 1. Plugging in 1 for x. It's the B part of the second one, the x2. I'm starting with this one.
Okay.
I didn't have to. You could have started with x1. Yeah. Okay.
That's 1 then.
Okay, what will that be?
1.
1.
B.
Not through. Minus
3.
Times
1.
1, which is 1 minus 3, which is
2.
Negative 2. All right. So f of 1 is negative 2. And we see that right down here. See, when you come over 1, go down, it's negative 2. Okay? All right. Now we need to do f of 0. And Ed, being really lazy, want to do that one first. Okay? Because it's so hard to do. Okay? And what would that be?
0.
It's 0. 0 minus 0 is 0. Okay. And sure enough, there it is. X equals 0. Your y is equal to 0. Right there at the middle. What's your average rate of change there then? Your x2, alpha of x2 was this. Negative 2 minus, and what is your alpha of x1? 0. I think I can even do that one. And then your x2 is 1 minus x1 is 0. Okay, I know I can do that one. What does that give us? Negative 2 over 1, which is negative 2. And sure enough, from 0 to, down there, you're going downhill, negative slope. Okay. And by the way, it sort of snuck up on us here, but you notice that when the, remember what we were doing just a few minutes ago? We were talking about increasing and decreasing. When you're increasing, your slope is up. Positive slope. And when you're decreasing, your slope is down. A negative slope. Hey, this is sort of making sense, isn't it? This, oh yeah, no, you know the math, okay. It snuck up on us, and sure enough we have it. Increasing function here, decreasing there. Now, was there a question? If you had chosen a point over here, on average it's increasing there, even though the function's increasing here and starting to decrease, you still have average increase. Okay? So you can't always go by that, but you can part ways anyway. Sorry. Okay. All right. That was example 6, and I think, well, let's see. We've messed with it. Let's see what they do. Average rate of change of F from x1, which was negative 2, to x2, which is negative 1, is alpha of x2 minus alpha of x1 over x2 minus x1, exactly like y'all told me to do, which is alpha of minus 1, because that's your x2. See your alpha of x2, there's your x2, so that's what you put in here, okay? And then, let me change colors. Green, why not? Well, green, why not? Okay, your xy, alpha of x1, you choose this one and plug that in here, okay? Alpha of x2 minus alpha of x1 over x2 minus x1, that's, oops, that should be the black one, okay? That goes here, and this one goes there, okay? So that's what you're doing with my messing up their pretty slide. And when you do the calculations, okay, they didn't show you how to do them, but we did them. Alpha minus 1 was 2, minus alpha minus 2 was minus 2, and 2 minus a minus 2 is 2 plus 2 is Whoa, 4. Didn't know we'd be doing such high-level math today, did you? Okay? And then in the denominator, minus 2 minus 2 is minus 2 plus 2 is 1. Minus 1 plus 2 is 1. So that will give you 4. The secant line has a very strongly positive slope. On the second part, your x0 was, your x1 was 0, your x2 was 1. So x2 minus alpha of x1. Alpha of x2 minus alpha of x1 is alpha of 1 minus alpha of 0 divided by 1 minus 0. I can do that. 1 minus 0 is 1. Your alpha of 1, if you plug it in, you get a negative 2. Alpha of 0, plug that in, you get a 0. That gives you negative 2 over 1 is negative 2. There you have a negative slope between those 2 points. Make sense? All right. Do we have time? I'm afraid not for even and odd functions. So that's going to have to wait till next time. So we'll start with even and odd functions next time. Let me give you some homework exercises. I know you don't want to leave home without them. Okay, or leave class without them. Okay. Let me mark my place so I don't lose it. We're almost through with 1.5. We'll finish it next time and move on to 1.6. Going awfully close to quiz time. In fact, I'll probably give you the quiz next time. All right. Do number 7 or 9. They're both at calcchat.com. 9 is at calcview.com. Do 11 or 13. They're both at calcchat. 11's at calcview. Do any of the odds 15 to 25. They're all at calcchat. 25's at calcview. Do any of the odds 27 to 31. They're all at calcchat. None of those are at calcview. Do any of the odds 33 to 39. They're all at calcchat. 35's at calcview. Do any of the odds 41 to 47. They're all at calcchat. Do any of the odds 49 to 53. They're all at calcchat. 51's at calcview. Okay, I think, all right, yeah, try to do any of the odds 55 to 59. We really didn't do one exactly like that, but you should be able to do it. They're all at calcchat, 57's at calcview. Then do average rate of change, 61 or 63. 61's at calcchat, both of them are at calcview. And we'll hold off on the others and pick those up later. Okay? That's pages 56 and 57. Yeah. All right. Any questions? Good deal. Then we'll see you on Thursday. Okay.